Dr. Lakeh from California State University, and also I want to thank you for taking the time, sharing your research with us. We look forward to continue the dialogue with you, and maybe have some collaboration in the near future. And I will also, want to acknowledge my colleague, Dr. Sherry, for inviting you. And also, I want to request him maybe, because you know each other longer than I do, so maybe he can, Dr. Sherry, don't mind introduce our speaker,
Sure.
And then we'll move on to the presentation today. Thank you.
Sure. Thanks, Dr. Shu. So I'm pleased to welcome Dr. Reza Baghai Lakeh, who is the Associate and Graduate and Program Coordinator in California State Mechanical Engineering Department, California State University, Pomona. And he has extensive research expertise and track record in thermal fluid science, energy system, and energy storage system. And he has published more than 50 papers in prestigious journals and conferences. He's the member of the American Society of the Mechanical Engineers and served as a chair in several conferences related to ASME. And today his talk is about the thermal investigation of using desalination concentrate as a low-cost thermal energy storage. So, Dr. Lakeh, please. Thank you.
Thank you very much, Reza, for the introduction, and it's a great pleasure to be with you today virtually. I hope you guys are having a good week in DC. So let me start talking about our project I'm going to give you a brief presentation that touches on all aspects of one of the projects that I have been exploring for the past couple of years. And it's now to the stage that we have formed a startup company so that we can transfer the technology out of the lab through a tech transfer process. So my name is, as mentioned, Reza Lakeh. I'm at Cal Poly Pomona, and I also work with Aaron, which is the co-founder of the Waste Salt Technology, the company that is going to help with the tech transfer. So in this project, Aaron is currently also a CEO of another water-related company called WaterFX, which works on solar desalination. We have been working on the support of the Bureau of Reclamation, and there are some partners and advisors from different institutions that helps us in this project. So far, we had, I believe, more than 30 students on different aspects of this work. But so far, I have about 8 or 9 master's students at about 8 undergraduate students who are doing their senior project on different parts of the work, and the graduate students are working on their master thesis or project. So let me get us started and first give you a 10,000-foot view about what we are trying to achieve in this project. We are tackling 2 major challenges facing water and energy industries with one single solution. So we are repurposing the desalination salt, we call that the waste salt, as a thermal energy storage medium to reduce the cost of energy storage. Our solution recovers about 90% of water desalination concentrate through a solar thermal process and repurposes about 100% of the salt for thermal storage. If this project is successful, then it will lead to more capacity for desalination plants, and it will also lead to cheaper solar energy if successful. So now I'm going to dig more into each of these problems that we're trying to solve here. Desalination concentrate management is a major challenge facing water industry both in the US and overseas. Discharge to ocean appear to be a commonly accepted method for concentrate disposal. However, this method is associated with adverse environmental impacts. The figure on the top right part of the slide right here that you see, you're looking at the salinity of the ocean surface and ocean bottom as impacted by the operation of Carlsbad desalination plant near San Diego. So this is the pre-operation and this is the post-operation, and you can see the effect of the outfall on the pH of on the salinity and the pH of the ocean water there. In fact, the Carlsbad facility is one of the hardest to work with because they are not willing to really cooperate as they're aware of this issue. So the change in salinity affects the pH, of course, and the water, it harms the wildlife. Without access to the ocean, concentrate disposal is a bigger problem, and it's a more expensive problem. The cost of disposal in areas where access to ocean is not present can be from 5 cents to 25 cents per gallon, according to Inland Empire Brine Line, a company that dispose brine in the Southern California. So just to put this in perspective, we should remember that even if the charge of this cost was 1 cent per gallon, that would lead to about $3,000 per acre foot of water, which is 3 times the cost of the water itself. So discharging and getting rid of this waste salt is an environmental challenge for water industry. Now I switch gear and talk about a totally different subject, and that's the need for low-cost energy storage. As you know, the future power grid will rely on intermittent renewable sources as we move towards more solar and wind. For example, California and 10 other states, they are targeting 100% renewables by 2050. In fact, California requires additional 50 gigawatt of long duration storage for keeping the power grid stable, because there are 2 different issues here. One is the intermittency of the source of the power, and the fact that there is overgeneration in the grid during the solar hours, and the need for storage during the peak hours. As you can see in this chart, this is called the dot chart of California. Excessive solar power generated during the day creates overgeneration risk. So you have generating too much power because there's too much solar energy being generated here, while there is a huge demand to meet later in the day. A storage device that we could have like this would store the energy, excess energy, whether it's solar or excess electricity in the grid, or the industrial heat that is wasted of a power plant, that can be stored in a device which can later on either generates electricity or generates heat for use. The Department of Energy has several initiatives, such as Sunshot, that aim to make solar energy more cost-effective compared to fossil fuels. Sunshot initiative has targeted $15 per kilowatt hour for thermal energy storage. However, we know that for solar desalination, the cost of thermal energy storage should be a lot less than that for the economics to work out. So in short, we need to develop low-cost, long-duration energy storage systems, such as what you see here, that are able to receive energy in the form of heat or electricity and deliver back electricity or heat as needed. So more on thermal energy storage. The state-of-the-art of thermal energy storage is a 2-tank configuration that has been used in concentrating solar thermal power plants since 1980s. So it's not really something new in power generation industry. In these conventional systems, solar field heats up the molten salt up to about 560 degrees C, and the heated salt is stored in a hot tank, for future use. At night, this hot tank now feeds the power block, and the cold tank is stored in the other tank. The cost of thermal energy storage by this method is around twice the cost that the Department of Energy goals, mainly due to the cost of solar salt itself. So the solar salt is the mixture of sodium and potassium nitrates that are used in the storage medium of the conventional two-tank systems, and that's the cost that is projected and reported. Now, there are some emerging technologies which are very interesting to me, and it shows that there are some potentials for marketability of devices that store energy. So the emerging technologies in the field of thermal energy storage are developed by both big companies such as Siemens or small companies such as Element 16. Siemens and Element 16 are examples of companies that are vastly different in size, but they develop or are developing energy storage systems that are very similar. This fact suggests that there's a good market potential here. The figures show the similarities between Siemens and Element 16 energy storage system. The thermal energy is stored in volcanic rocks in the Siemens system, while the heat is stored in elemental sulfur in the Element 16 system. I would like to highlight that the material that these companies are using for thermal energy storage are cheap, abundant, and chemically stable. So now moving on to the market trends for thermal energy storage. Market forecasts suggest that the thermal energy storage market, both in the US and globally, will steadily grow over the next decade. This fact creates a huge potential for projects that try to use thermal energy storage. Okay, so this slide kind of shows under the hood of what we're doing in our project and how we repurpose the concentrate salt for thermal energy storage. So the desalination concentrate is introduced to a zero liquid discharge system, which will reclaim additional water. So if this is our reverse osmosis facility, the feed water enters, the brine or the concentrate is received here. There's good water generated, which is not really what we care at this point. We get the waste here, we further process it through zero liquid discharge, get additional water, and extract the solid salt. Then the solid salt is processed in a series of steps to enhance the heat transfer and thermal characteristics of it, both to increase and decrease the thermal conductivity for different layers that we have inside the salt tombs. The processed salt is added to a corrosion-resistant concrete, and a heat exchanger is implemented in the salt, as you can see schematically here. The salt and the heat exchanger are sealed to form a thermal energy storage module, or a salt tomb, as we call it. The heat exchanger provides the heat to the salt during the charge cycle and removes the heat from the salt during the discharge cycle. The design and configuration of this heat exchanger will depend on the salt composition and inherently will depend on the water chemistry of what is added to the desalination plant in the first place. Okay, so to wrap up, there are good benefits of using concentrate salt as thermal energy storage medium because it saves the planet, it prevents desertification, and it enables very low-cost energy storage. And we can repurpose it by minimally processing and store it and prevent it from um, releasing to the environment. It's a it has inherently negative cost because there are no major applications for the concentrate. In fact, it's a waste material that companies pay for the disposal. But the salt is very highly abundant, of course, inside in the concentrate, and it's very chemically stable. Some of the salts extracted from the concentrate go through phase change from solid to liquid at different temperature ranges, and that will provides higher energy storage density. Okay, in this slide, I would like to provide the history and vision, of the project, that where we started and where we are. We started testing the feasibility of using concentrate salt as a thermal energy storage medium back in 2018 by the support of Bureau of Reclamation Science and Technology grant. We expanded our work after receiving an additional grant from the Bureau of Reclamation to develop a lab scale demonstration and further refine our techno-economics model. And at this point, we are trying to raise money, apply for funding so that we can have a pilot scale demonstration of this concept. And that's something I'm currently working on. So now a little bit more on techno-economics and why it makes sense economically to do this. The cost of any thermal energy storage system that you can imagine will include the cost associated with the storage material and the cost associated with the containment. If we imagine water as a storage medium, which might seem obvious, the cost of the containment will be very prohibitive in high temperature, while the cost of the water would be very small. In the conventional solar salt systems, the cost of the material dominates the cost of energy storage, while the cost of the containment is a lot smaller compared to water due to lower vapor pressure of salts compared to water. Concentrate salt or waste salt after processing has a negative cost because we essentially receive that waste brine, waste concentrate, and charge the desalination companies. It has a negative cost that reduces the cost of thermal energy storage, even if the required processing costs of preparing the waste salt are considered. In the next slide, I'm going to put real numbers on these charts so you can get better understanding. So this slide shows the details of the thermal energy storage cost using the waste salt in different working conditions. The thermal energy storage costs are significantly lower than the state-of-the-art and Department of Energy's cost targets. The figure on the left shows the details of the techno-economics model that predicts the cost of thermal energy storage by various storage temperatures. And as you can see, we have quantified a lot of costs associated with processing the waste salt, including grinding, evaporation of the water, excess water, additives that are needed, the shell and the labor. So it's a comprehensive study. The figure on the right here shows how gain from desalination facilities can offset and cover a part or possibly all of the thermal energy storage costs, depending on the location of the concentrate disposal and other disposal options. So there are three categories, and these three categories are based on other available disposal options. There is a company that provides concentrate disposal in Southern California, and we use that numbers as our gain here. So these are the three categories of that company. If you directly use they give these three values for directly using that brine line, or having a truck service for the brine line to be disposed using the line, or very far away from the LA basin area. And as it creates here, the cost of the thermal energy storage can be offset using this gain. So we also did some a lot of salt characterization on different salt samples that we received from different locations within the Southern California. And we send the samples for water chemistry. We observed that the concentrate salt, which is a eutectic salt, melts at different temperatures. Some samples melt around 450 degrees C. Some samples melt around 650, and some samples did not even go through any phase change. And that's something that is interesting for us to observe. Now, the thermal physical properties of this waste salt in our work is either measured or estimated. In order to estimate a value for heat capacity, heat of fusion, and density of the waste salt, we developed a statistical model to predict the ballpark of properties based on the
I'm gonna show you your table one more. She's doing some magic.
Sorry, the audience, would you please mute your speaker? Thank you.
Thank you, Reza.
Sure.
No problem. I was saying that in order to estimate a value for heat capacity, heat of fusion, and density of the waste salt, we developed a statistical approach and found the weighted average of the properties based on the salt mixture composition. We also performed thermal testing on various concentrate salt samples to measure the temperature range of phase change for each of the samples, and this is an ongoing effort. We identified two commercially available tools that are very helpful for us, and they can help us to obtain the thermophysical properties of different salt mixtures. So OLI will provide us with the composition of the solid salt if we have the water chemistry of the concentrate. Depending on the pH, then there's a lot of chemistry and chemical engineering involved in there, which we're relying on the OLI. And from there, ANSYS Granta database provides a lot of thermophysical properties for salts, which we are also using. In the lab scale, we did one lab scale demonstration, and we're working on the second one already as we prepare for the next phase. In the lab demo, we developed and tested a 5 kilowatt-hour system that stores thermal energy in a single element configuration. We received reverse osmosis from Eastern Municipal Water District, extracted the solid salt, and packed the salt in a storage tube right here, and then configured a test setup and basically, they wrapped everything around insulation and test the system in a cycling manner, in a cyclic manner, and looked at the behavior of the salt after each test. In parallel, and this is most of the work that was done during the pandemic, we worked on now simulating this lab scale demo, and also looked into the phase change process that happens inside the tube, because we know that the salt that we have in the storage element here melts about 450 degrees C. So we developed a computational model for that cross-section area of the tube here. This is the work that two of my students worked on, Justin and Chris. And they used ANSYS Fluent to solve the governing equation of the flow, and they did some verification using mesh refinement, grid refinement, and also some validation in comparing the computational results with lump capacitance method, and the agreement was good. So we could model the phase change process inside the tube and get an idea about how effective the heat transfer can be for this thermal storage process. One thing we learned here is that there is a need for treating the salt with low-cost additives to enhance the thermal conductivity and reduce the charge time here. So we got some non-dimensional analysis to characterize the convection currents inside the tube, and also we did some analysis on what would be the lifetime of a system that's made by a system like this. We concluded that the major failure that could happen in a system that's shown here is by corrosion of the heat exchanger element. That's the major failure that could happen. And by adding some corrosion resistive linings to common alloys like stainless steel, we hope to reach low corrosion rates and have a lifetime of about 20 years. Even though after, let's say, one of these modules, one of these salt tombs fail, the only thing that should happen is that the tomb is opened and the salt is maybe processed again, and an additional heat exchanger is added right inside the tomb. So there is no need, or the salt be repurposed again for the same purpose. Now, in our next phase, we're collaborating with WaterFX, which has a solar desalination facility already in Panoche, California. So in Panoche, California, which is located, right here in the middle of state. I don't know if you haven't been to the Central California or not, but it's nothing like the beaches. So it's a agricultural land, and it's has a lot of water shortage issues. And so this demo of WaterFX is already done there, but one of the major problems and the reason that their economics didn't work was that they didn't know what to do with the salt that they generate this, and that would lead to excessive cost burden for the solar ZLD technology. So we hope that integrating that salt tombs as thermal energy storage module will create a path for the waste salt to be directly repurposed on the spot or be sent to other applications. So another broader impact, and I spoke, I guess, for 45 minutes already. So a broader impact that I want to bring up, and then I'll conclude, is that there is a lot of water in California brought from the Delta, the San Francisco Delta, Bay Delta area through the California Aqueduct. So a lot of water in the Central Valley and in Southern California is coming from the north. And the problem is the salinity of the San Francisco Bay is increasing as the income of the inland water is reduced and more ocean water is inserted, is moved or diffused to the bay. That salt of the ocean will come to the Central California and is now already increasing the salinity of the salt in this area. And for this reason, the agricultural runoff water needs to be treated so that it doesn't destroy the environment in that area. And this project can potentially help with that as well. This actually has been one of my most rewarding projects that I have since I started my career. We filed 2 provisional patents, published several papers, and won the Best Research Project award of the California State University competition. And we aim to continue this work in the pitch to pilot scale, in the next step in the pilot scale. Okay, thank you for your consideration and looking and hearing my presentation. I would be happy to answer any questions that you may have.
Thank you. So the students, if you have any questions, I encourage you to ask, and you can type in the chat if you like to do that way. And so I have just a quick question regarding what you mentioned regarding the corrosion for the pipes. I saw you mentioned there was an article in 2017 talk about some materials can be used for that. So so besides this particular material, is there any study on like adding certain coating or just maybe, I mean, this apparently metal is preferred in this case for the heat transfer purpose, but I just wondering like what other approaches has been studied regarding to reduce the corrosion for those pipes.
We looked into several options, and this is an ongoing thing, but there are two competing factors. There are technologies that you can reduce the corrosion, but for the scale of the heat exchanger, the cost will be, dominant and will damage our economics on one side. So, but there are some other options, some additives that can reduce. But at this time, I think what we know about corrosion is that it's a manageable problem, because there are other industries that are using salt. The solar thermal facilities use salt for decades, and there are ways to manage the corrosion. But we don't know exactly like what is the solution there at this point.
Okay.
Mhm.
Okay. Yeah. So yeah, definitely the cost, yeah, for this type of application is a huge consideration. Yeah. So for your work with this company, right? Um, I guess this for just for the students, I guess. What is your experience? What's your kind of because you are a professor at the university and you're working with a company and you have students involved. So what is experience? What you would say to those graduating seniors? What they need to understand, what they need to learn. The critical things before they graduate, before they, if they want to find an industry job, what the critical skills they're looking for.
I think this is the advice that I give to my students as well, and is that as engineering students, we are too much stuck with the details and too much stuck with the technicalities to the level that other disciplines can use engineering as a tool and make money. But the business side of things is actually is exciting, is more exciting, and is more rewarding in one sense, and at the same time is not as complicated as the technical side. So in our experience, so we at some point when Aaron, the partner that I showed you, he found our project through the grants and approached us, and we formed the company and included the students, and the goal was to, okay, now this project cannot go to the next level if we are limited by the bounds of universities, because the time of our time is limited, the facility is limited. So if the concept can get to another level, there should be an entity focused on that. And then we formed this company, and we're trying to raise money for the company, which part of that will go to university to support some of the efforts there. But still, now we have more freedom of like approaching and talking to investors. There is a lot of how to say that there's a lot of paperwork and bureaucracy involved in academic settings, which you can have freedom from if you work as an independent startup. So my advice is to look into entrepreneurship, look into what are startups, how are they formed, how are they funded, and there's plenty of materials out there to to learn about that. And one interesting opportunity by National Science Foundation you're probably aware of is the I-Corp opportunity, which helps you. But basically, they fund your project so that you can find the right customer, and the student can play a good role in that.
Yeah, great, great. Thank you. I think for us, we need to do better on this. I think we have been trying to integrate the entrepreneurship mindset, to our curriculum. I think, there's more work that we need to work on. We need to, provide to our students. I think California in particular has been, I think leading, in the country, providing those, incentives for entrepreneurship in those technology incubators. So that's great to see, you're able to develop your research in a way that can, work and potentially, be something that the industry can apply. They can utilize the technology, right, for something that can benefit a lot of people. That's great. That's great. So I'll stop here. I'll let other people to ask their questions. Please, please feel free to ask our speaker any questions you have.
Yes, I have a question for you. First, thanks for presenting to us today. That was good information. I didn't know about this application of being able to use waste salt or desalination salt for thermal storage like this. My question is, we just got assigned our teams in our senior project group, and I was wondering, in your experience of developing this product, were your teams more so focused on dividing each part of the product or project, and then each part of a team working on a part and then putting it together at the end, or dividing it into parts and everybody working on it intermittently and then coming at the end up with a solution to problems, or like a product at the end?
Beautiful, very good question. So we have some committees, like we have three major committees: the techno-economics committee, the lab committee, and salt characterization committee. And a fourth committee, which is the technology to market. And the students are they have one major committee, which I expect them to contribute the most, and one secondary committee, which they contribute less. And at the end, most of the time, the outcome of the work of these committees will be a publication, or will be a presentation, a poster or something, and the people who were involved in that will be, of course, the co-authors. And so in this framework, the senior project team may be doing different things, but they're contributing to the bigger picture here.
Okay, thank you.
So, Reza, I have a question. Very exciting, and thank you for nice presentation. It's always good to see application-based projects. So, how do you envision in next, because you show some numbers, and we see also in the news that mostly European countries are changing or going into the renewable energy, and United States, California is the pioneer on that. How do you envision, if we want to replace the current technologies that we have and to replace with the renewable energy? How do you see these numbers, these years achievable, for example, next 20 years?
You know, frankly, let me show you something. So this Sunshot initiative, when I was when I was a postdoc at UCLA, this program was started, and they had a goal of 2020 back then. And back then, this goal, the goals here, you can see their achievements later, but their goals, they not only met the goals, they exceeded the goals in most of the cases. Now they have more, like the goal was to reduce this number to 6 cents per kilowatt hour, but it's already almost there. So I would say it's possible, may not be exactly by 2050, but it's probably somewhere in that time, you know, plus or minus 5 years maybe.
So you are optimistic about this trend. So that's.
Yes, because you know I think the climate change is already you know is already here, and I think most of the people already felt its presence, and as long as there is you know funding, federal funding to support these efforts, I think these can continue, and these numbers, these estimations can be met. But in general, there is another aspect to it, and that's the need for technologies that are not yet developed, like energy storage. This is something that is still developing, but the hope is we can get to the numbers that we expect by 2050.
So another question that I have for you, maybe that's good for students who want to select their major for their career. So do you see, I mean, definitely there are that if there, I knew I would work by myself on that, but definitely there are some research that must make themselves compatible with this trend. There are some. So are you still working on those? Are you trying to find out the new areas that, for example, say buy to the previous technology and hey, this is the new technology for example, changing the cooling systems or changing the systems that are working previously with other kind of energy, but right now they have to adjust themselves with the renewable energy. Do you see this as a long-term research for the new research area that will be created?
I think honestly, we will move towards a grid that is more, it's 100% renewable.
Right.
That's the direction. So the normal user, the normal application will not really feel the change. Only the source of the electricity have changed. But the technologies that need to be developed to provide that 100% grid, you know, renewable energy. I'm not sure I understand the transition that you mean for those companies, like for
Not
the
companies. For example, just as an example, if I want to say the electric vehicles, if I want to say that if we want to change to completely electric vehicle, there are technologies that right now are working with the fossil fuels. And by changing by replacing this fossil fuels with the renewable energy, the existing technology will be gone because they no longer will be used by the renewable energy. So my question is about this transition. How smooth do you envision is that, or do you really finding new approach, new research areas that are, because they are very exciting for us. We have a, I would say, good credential and potential here, and we try to find out a way for the collaboration. And you are definitely one of the, your research is one of the exciting research. I see some excitement in our group. So I guess my question is that we are finding the new research areas. So are you aware of any things that right now currently are adjusting themselves with new markets that people are working?
I know there is a huge need for hydrogen extraction technologies, for example, that you know, we could possibly work on, and that's kind of maybe the transition that you're mentioning.
Right, right.
Yeah, and there are different methods that are developed, and it could be many of the findings of academic work, as you know, they stop at publication, so they're never taken beyond that. So there are many technologies that, if we can have the intellectual property of that, if we can license the intellectual property of that, then it's something we can continue work on and develop demonstrations and then try to receive funding from venture capitalists. Yeah, but there are definitely opportunities, and I would be happy to continue working with.
Oh,
with
definitely.
You
That's great. Definitely. So definitely we'll be in touch, and I'm pretty sure our students would be excited also regarding this collaboration. So Dr. Shu.
Yeah, thank you. Yeah, that's great. So definitely look forward to collaboration on this. I think a lot of areas that we can collaborate on regarding just in general, energy storage, renewable energy. Yeah, we do have a renewable energy concentration for our mechanical engineering undergraduate program. So definitely areas we can collaborate. I see a question here from a student. Maybe I'll read it here. He was wondering, has any of your students considered doing a STEM MBA degree? Not quite sure what is a STEM MBA, but yeah, if we can answer that.
Yeah, I have a few students actually. They continued with an MBA after they do their bachelor's or the master's. Yes, they do that. They're not part of the project currently, but in the past I had some students who did that.
Yeah, I think one thing we have, at least we had some discussion on, we call it 4+1, which is 4-year STEM, and then 1-year MBA. I don't know the current status, but I think that's something maybe worth pursuing, to provide those opportunities to the students. Yeah, so.
Absolutely. Yeah.
Great. Any other questions from the students? I see a hand, Doreen. If you want to ask, you can just unmute yourself and ask directly, or you can type in the chat.
Okay.
There's a question. Go ahead.
Can you hear me?
Yes.
Yes.
Okay. Well, one, I think this is a really great. I think this type of energy storage, transition is really important, especially when you start thinking about climate control and things like that. And I'm not sure if some of the other questions kind of touched on this, but can you see something like this type of system being, going into a global type of, type of energy usage or system?
Yeah, very good question. In fact, there is a project in Saudi Arabia in the Middle East called the City of Neom, and it's one of our targets because they fund projects that are in earlier stage. And in global stage, it's actually more appealing because there are some areas in the world that the ocean salinity is so high that you cannot really dump that extra concentrate because that will be catastrophic for the wildlife and environment there. For example, I think near Mediterranean seas, there are areas that have that characteristic. So for those areas, in fact, something they happen to have a lot of sun and a lot of solar thermal heat that can be used. So yes, we looked into that as well.
Okay, that's great. I guess the reason why I asked because I've been doing some research as far as you know like the certain energy consumption of certain countries, and it just seems like a really good system that would help in the reduction of that. And I feel like with that, moving in towards the future could really just overall help globally.
Mm-hmm. Mm-hmm.
Great. I see there for two more questions here. So one is asking, at the end of the thermal energy storage life cycle, can the salt be reused in a new device?
Yes. So, in fact, after the lifetime of the module is over and there is a failure caused mostly by corrosion, then the salt there can be, you may have to, we've never really done that, but that's what we expect, that the salt there needs to be reprocessed again, maybe packed again, maybe additional salt be added, but it can be most likely be repurposed again there. And in fact, the deposits of the metallic, you know, heat exchanger surface to the salt will cause better thermal characteristics, will increase the effective thermal conductivity. So it will have its benefits as well.
Yeah, and there's one more question, I think is for the additives, for the was the additive mainly to lower the thermal conductivity, melting point of the solution?
Okay, good questions. Good questions now. So we treat salts in two different ways because this is the new design we're having, and it has an inner layer and outer layer. The inner layer is treated to have more thermal conductivity where the heat is stored, and the outer layer is treated to have lower thermal conductivity to act like an insulator. So did I answer the question at all? Was this a chemical process? So no, it's not a chemical process. It's just adding silicon oxide or some nanoparticles or aluminum oxide to increase the thermal conductivity, and some rubber-based additives to the salt here to reduce the conductivity. I see another question here. Can we guarantee that this new device help reduce pollution? I hope so. I really hope so. I don't know, but I hope so.
Yeah, that's part of research, right? No
So
guarantee.
Dr. Reza, as you see that we have lots of interest in your research. So I think that's a very good suggestion, Dr. Shu. We again asked Dr. Lakeh to present later with the new project, because I personally very excited about what you presented. So that's a very, very match with what I think Dr. Shu also has some experience in nanofluids. So I was expecting he has some questions regarding the but it's very, very exciting. So hopefully we keep this momentum and we keep this collaboration alive. So we bring you again here next time you come to the campus and see our facility and see what we can do as for further collaboration. I see some application in additive manufacturing. So we have a very advanced 3D printing machine, 3D printer here, and some facilities in nanofabrications, so nanoscale devices. So hopefully we can extend the collaboration.
Absolutely, it would be my pleasure. In fact, we recently formed a virtual speaker series like what we have, what you have here, and I'm going to invite you faculty to that event.
Definitely, our pleasure. Thank you.
Yeah. Great. Thank you. Thank you again for sharing your research with us, and look forward to have you maybe here in person in the near future, and also more collaboration.
I would be happy to.
Yeah. Thank you very much. So I guess I will conclude the virtual seminar here today, and for the students who are in the class, you can stay on, and the other students, yeah, you can feel free to leave, and yeah, so we'll conclude here. So Kevin, if you are on, you can end the recording. Yeah.
Thank you, Reza. Thank you.
Bye.
Yeah, thank you. Bye.
Bye bye.